We have to do everything over Wi-Fi now. Okay, great. So welcome everyone to this term's lecture. So my name is Stefan. I'm a group leader here at the PKS, at the Max Planck Institute for Physics of Complex Systems. And we have quite a few people. So normally our lectures have like maybe 10 people most, and that's because we're a research institute. Yeah, and that means we normally don't do a lot of teaching because we don't have to, but sometimes we do it once in a year or so just for fun. And this lecture is in the same spirit, that we're trying out something new, that we're giving a lecture for fun and see what comes out of it. Yeah, so to start, as we saw, we already had some technical issues. That will probably be a common theme for the rest of this lecture. And some of these issues will be sorted out by Yuteng, who's here in the room with me, and who's the only person in the room at the moment, because we're, as everybody else, we're back in lockdown. And Yuteng is probably at the bottom of the list. You can write to him in the chat in case you have any questions or anything else. Just write him if you can't hear me. Then just send them a message. Okay, so I'll share my screen. You should still be able to see me. Yeah, so this is the lecture, and today I would just like to give you an overview of what all of this is about. Yeah, and to give you some information that allow you to decide whether you want to follow the lecture for the rest of the term. Yeah. So I guess there are quite a lot of people that are dialing in from abroad. Or from even India, I've seen. And so just to let you know where you are at the moment, so you're joining a lecture that is taking place in the Max Planck Institute, MPI PKS in Dresden. And this Max Planck Institute is focused on theoretical physics. That's Max Planck Institute for the Physics of Complex Systems. We're doing theoretical biophysics, we're doing condensed matter physics, and also atomic physics. So these are the three branches of this lecture. And we're covering all of these aspects from the perspective of theoretical physics. Yeah, so you can see it's quite nice here, although Dresden is a little bit in the corner of Germany. So sometimes a little bit difficult to get here and to get out, which turned out to be a benefit in the times of coronavirus. So this is the Institute, and to start this lecture, to give you an idea of what we'll be doing this term, I'm just showing you some of the kinds of systems that will be covered, at least in spirit, in this course. Now, what you see here are three examples of systems that all share some striking spatio-temporal structures. And all of these structures arise because there are some microscopic or some interactions on the small scale. On larger scale, on macroscopic scales, then these interactions lead to some interesting phenomena, to the emergence of order. And the left-hand side, you see a swarm of fish. I forgot the name, but what these fish do, they rotate in these torus structures to distract predators. That's what they do, and these interactions are just a result of alignment interactions. So, all right, I hope you can see that. So on the microscopic scale, each fish aligns its velocity to some fish in the neighborhood, and on the macroscopic scale, you then get this swarm. And the second picture, it's another example of collective processes. That's the emergence of traffic jams. So you have in traffic, you have the phenomenon that traffic jams arise spontaneously. And these spontaneous traffic jams are a collective phenomenon that arise from interactions between individual drivers, and in particular, how they break in response to changing velocities of other drivers. So on a microscopic scale, we here have changes in velocity. Yeah, and out of this, you get a macroscopic phenomenon on larger scales due to these interactions. That is this traffic jam. Yeah. And on the right-hand side, you have a third phenomenon. Yeah, that's taking place on much smaller scales. Now, that's what you see here is what's going on inside a cancer cell, and what you see is the cytoskeleton. Yeah, and what you see here is long fibers, macroscopic or mesoscopic fibers of molecular assemblies. And these fibers are also built by dynamic processes of proteins attaching and detaching from these fibers. So here, in this case, you have molecular interactions that give rise to macroscopic structures that in the end then control the shape of cells and also partially their movement. Yeah, the cytoskeleton. Now I apologize for my handwriting. So I'm waiting actually for a very nice 12-inch iPad, but it was not delivered yet. So now I'm in the unfortunate situation that I'm writing just on a 10-inch iPad, yeah, which is of course much smaller, and that's why my handwriting is a little bit not that good. Yeah, but that will improve over the course of this lecture once the delivery comes. Yeah? So these are the three examples, and in all of these examples, physics has played an important role in understanding these collective processes. So why do we need actually physicists? Why do we need to study to understand collective behavior in such systems? Maybe an even simpler example is water and ice. Water is made of water molecules. We know exactly what water molecules do. Now we can probably solve the Schrödinger equation for a single water molecule, at least numerically. Yeah? But once you put these water molecules together and you lower the temperature, you get ice crystals. And if you zoom out even further, you get these complex structures that are snowflakes. And these patterns that you see here in these ice crystals are in no way in the Hamiltonian that describes the quantum dynamics of a water molecule. Yeah, and what that means is that, for example, the water molecule is of the Schrödinger equation is rotationally invariant, it's translationally invariant. Now you can retain the Schrödinger dimension and the Schrödinger equation, you still get the same behavior. These macroscopic structures here, these ice crystals, they don't obey the same symmetries. So we have symmetry breaking as we put these water molecules together and let them interact. And this symmetry breaking is often called emergence and gives rise to the complexity that we see in nature and in biology and also in social systems. Yeah? So the macroscopic behavior of such systems does not necessarily obey the laws that govern on the microscopic scale. The macroscopic structures don't follow the same symmetries as the microscopic description, such as the Schrödinger equation. Yeah? If they did, everything was easy, and nature would be pretty boring as well. So that means that these macroscopic structures follow different laws than govern on the microscopic scale, and we need sophisticated tools from statistical physics and non-equilibrium statistical physics to connect these different levels, these different scales, to connect the microscopic interactions to macroscopic phenomena. Yeah, and that's what a large part of statistical physics is about. So at the same time, in recent years, we probably became aware of that this whole thing that's called big data. Yeah, so we're now able to study complex systems with unprecedented detail empirically. Now we can take measurements in quantities that were impossible a few years ago. And one example is of course social systems. that underlie, of course, for example, the spreading of epidemics. So, for example, if you look at what these people do that do COVID modeling, so they take into account traces. You have these apps, right? They trace your movement, they trace your interactions, and you have all of these data on the level of very high microscopic resolution of single individuals. Of course, you test people, you trace them, you know who is infected, who is not infected to some degree, and then you also know who is interacting with whom else. So you know something about the social interactions, think about social networks like Facebook and so on. You have huge data available that describe social systems on the scale of individual interactions. And of course, now that there are elections in the United States, the same is of course also true for elections. So in recent years, it has become increasingly clear that people hire big data companies that digest all of this data about voter preferences and so on to make predictions about what are the best counties to approach and so on. And that's certainly true for the US, but also for the UK. Another example of where such high dimensional, huge data sets emerge is in biology. In biology, we have seen technological breakthroughs in recent years that now also allow us to study biological systems in unprecedented microscopic detail. Now, there are several technologies that imaging involves, but one of these breakthroughs was in genomics. That's also something we're working on in the group. So these breakthroughs in genomics now allow us to measure the state of individual cells, the molecular states of individual cells, with unprecedented detail that was not possible before. Now, as you see here on this slide, you see an example of such an experiment. Now, that's actually was conducted by collaborators in Cambridge. And so here you see information, just a part of this information that is gathered in these experiments. And what you see here are measurements on individual positions of the DNA. Now, that's what's on the x-axis. So the x-axis here gives you the position on the DNA, in the genome. And for each of these positions, for each of these molecules that the DNA is made of, you can measure whether there's a modification of this molecule or not. Now, that's what you see in the bottom half of this plot, and in this top half of the plot, you can measure something about how the DNA is folded in this region of the genome. Now, if you download such an experiment, that comes with like a terabyte of data as well. So that's a huge amount of data, and you cannot only do that for a single cell, but you can do that for many different cells at the same time, and that's what's on the y-axis. Now, so on the y-axis are different cells taken from an embryo, and here we in principle can measure the molecular state of cells, of all cells from early mouse embryo. And that's in physics not something that we do very frequently, right? We don't start an experiment and measure every single spin in a magnet. We don't measure every single velocity of particles, of every single particle in a gas. So that's not typically how we think. We do macroscopic measurements. In biology and in social sciences, we can now approach these systems on a microscopic scale with almost arbitrary details. And that, of course, gives rise to questions about how do we connect these two developments. So how do we take such large data sets and translate them into understanding of collective processes? So why would you actually want to do something like this? So if you describe something, if you can measure everything on the microscopic level, why do you actually want to understand something? Why are you actually interested in these collective processes? And the reason is actually very well depicted in this car here. If I give you a list of the microscopic parts a car is made of, you would have a hard time understanding how this car works or how an engine works. And of course, how this works, how this car works, is not a property of all of these individual screws and tires and so on. It's a property of how all of these things work together. Now, so the function of this car depends on how they work together, and how they work together is not immediately, you cannot immediately deduce from listing all of the parts, or measuring all of the parts the car is made of. And the same also holds true, of course, in biology. A biological function does not rely on individual molecules in the cell. The biological function relies on how these molecules work together and then have some macroscopic or mesoscopic consequences. Yeah, and this is exactly the question that we want to address in this lecture here. So how do we, what are actually the tools that we need to understand, that we need to know in order to identify and to understand collective processes, collective behavior in systems that are out of thermal equilibrium. Yeah? And traditionally, so people like me and probably many of you, we've been educated in equilibrium systems. We had statistical physics lectures and statistical mechanics, maybe statistical mechanics too. So that deal with some very specialized cases in so in internal equilibrium. So a gas that is somehow isolated or that is in contact with some heat bath or so. So these are very special cases. And we then try to use our understanding that we gained in our statistical mechanics lectures on criticality, phase transitions, and so on, and we try to transfer that to non-equilibrium systems, so the whole rest of the systems that are out there. Yeah, and that's what we do, and it actually works quite well. So we're making some, of course, we have developed tools, also non-equilibrium physics, but our intuition was typically trained in equilibrium systems. And so the goal of this lecture is actually to identify what is actually the intuition that you need, what are the tools that you need in order to derive these collective properties of systems that consist of many interacting particles. And that's a two-way road. So we, on the one hand, we have these high-dimensional data sets, like the ones that I showed you. And the question is, how do we treat these data sets in order to derive theories, in order to build hypotheses? So how do we actually treat these data sets? How do we derive a hypothesis? How do we understand the structure in such highly dimensional rich data sets? And so that is that we will need some tools from data science. How to deal with data sets that, in the case that I've shown, have millions of dimensions. The reverse direction is actually, how do I understand order from microscopic theories? And these tools that we need for that come from non-equilibrium statistical physics that then allow us to make predictions from theories that allow us to infer how do we, once we have a theory, once we have a microscopic description of a biological or social systems, how do we derive collective processes from this? How do we derive collective degrees of freedom from this? So these are the two ways that we will deal with in this lecture. And so this is how it will work in practice. And so we will start with a basic introduction into stochastic processes and also field theory. So it would be good if you could give me some feedback. So I don't know how many people are we now. Oh, 63. Okay. So it would be good if you give some feedback. What's actually your background? So on the website, and I think on Twitter, I don't know, and on the website, I said that what you need is a basic understanding, or not a basic understanding, but you need to have a statistical physics lecture. Yeah, so you shouldn't be shocked or shouldn't be the first time that you hear what about a phase transition. Or shouldn't be the first time to hear about entropy or so. Yeah, and so it's a statistical physics lecture, and building on top of that, then we introduce some things that we can't rely on, having been told in statistical physics lectures, which are stochastic processes and non-equilibrium field theory, so path integral representations of these stochastic processes. And then we go on and ask, how do microscopic interactions lead to macroscopic order? Actually, I have a little torch here. So how do microscopic interactions give rise to macroscopic order? And of course, there's no general theory for this in non-equilibrium systems. We don't know how this works in general, but we can use some instructive examples that would, like in statistical physics and equilibrium statistical physics, would be the Ising model. That's a very powerful example for second-order phase transitions. And we'll deal here in the second part with some very powerful examples of non-equilibrium systems, of how order arises in non-equilibrium systems. Yeah, next we'll go on to study transitions between these ordered states, so non-equilibrium phase transitions. We'll introduce renormalization group theory and talk about non-equilibrium criticality, and look at some very specific phase transitions, so-called absorbing state phase transitions that are very relevant for epidemics. Yeah, and actually we'll have a few examples from epidemics in this lecture. Yeah, so next we ask the reverse question, the reverse error, and how do we actually identify such collective order in data sets that come with terabytes of size and 10 million dimensions? How do I actually identify, how can I actually efficiently on a computer deal with these kind of data sets? And how can I use statistical tools for machine learning to break these, to identify structure in such data? So we'll have then some applications from real research, and finally, as a bonus, we'll ask the reverse question. So not how microscopic order gives rise to microscopic interactions give rise to macroscopic order, but we'll ask, how does macroscopic order shape microscopic states? Yeah, so that's the reverse question. It's a very new question in the field, but that has some very interesting application, for example, for neural networks. Yeah. So this is the structure of the course, and I'm actually very happy also to adapt to your needs if time permits. Yeah, so just send me an email if you have any questions or anything else. Yeah. So you have prerequisites, statistical physics. Yeah. So we make use of functional analysis. Yeah. So that's typically taught also before statistical physics, I think. But that's a helpful tool to need. But if you don't have that, it's also enough to I'll introduce that quickly in the lecture. Yeah, field theory is also helpful. I don't give a rigorous introduction to field theory or to field theories in general, but I'll introduce the field theories that we need here for this specific course. But if you know already some field theory, you'll see that things are actually quite similar to field theories in quantum field theory. So in quantum systems, for example. Yeah. So literature, so it's actually a problem, yeah, because there's no book that tells you exactly the story that we want to address in this course. And I'll give you some literature for each of these sections that we're going to deal with. Some generally quite good books, especially for the first part of the lecture, are the ones by Eltland and Simons, condensed matter field theory, that covers this field theory aspect, that non-equilibrium field theory aspect. And the same book by Kamenev on non-equilibrium field theory basically covers the same perspective from a more quantum point of view. Yeah, so that they're just dealing with it for one part of the lecture. And so this lecture is generally, as you know, taking place Tuesdays at 4:40 p.m. CET. And we'll ask typically for 1.5 hours, but I'm a little bit hesitant to talk for 1.5 hours on Zoom because I know how tiring this can be. And so what I'll do, I'll have the content of a 1.5 hour Blackboard lecture, but usually because of this iPad and so on, we'll cover that stuff in a quicker time because I don't have that much writing. And but in terms of calculations, I'll always write them on the iPad, so I'm not going too fast through them. So that's the lecture, and then there's a website. So I can't remember the exact. That's the group website, and if you go to teaching, you'll see a link to this course, and I'll upload, if technology permits, so I'll upload first the slides, so PDFs of what is written in the lecture, and I'll also try to upload the videos of the lecture. I can't promise it for this one because I have to just hope that it works. And but I'll also post links to videos, at least starting with the next lecture, when I figure out how all of these things work here. Okay, so to start today, to take down the clock, to start today for the rest of the lecture, I'll just give you a brief reminder of actually how we can see that a system is out of equilibrium. So the kind of systems that we're dealing with in this lecture. And the simplest answer you can give is that any system is out of equilibrium. So you have to have very, very extremely special cases where systems are actually in thermal equilibrium. And anything you see in biology, for sure, and also in social systems, is out of equilibrium. So the question is actually already answered in this way, that everything is a non-equilibrium system. But given that we learn statistical physics typically in equilibrium systems, just let me make sure that we all are on the same page, understand what it means to be not in thermal equilibrium. So how can we be out of thermal equilibrium? And why is it important? The first thing is, what you can do is, if you look at these plots of these pictures that I showed you previously, at the beginning of the lecture, the fish swarm and so on, there's one thing that's already strikingly clear if you have listened to the statistical physics lectures, is that something's wrong with the second law of thermodynamics, apparently, right? So the second law of thermodynamics basically, in a very rudimentary way, states that entropy increases in systems that are isolated. And they approach some equilibrium state with maximum entropy. And that's obviously not the case for the systems that I showed you. So they're not in this state that you would assume to be in thermal equilibrium, and because they're very dynamic and highly structured. And the reason, so how can you break, so to say, the second law? So I hope they're not like hardcore statistical physics. I always have the quotes. Of course, the second law is correct. So one way you can avoid this is that the system is just not isolated. And one of the conditions for the second law. The first thing is the system is isolated. It's isolated, but it hasn't reached equilibrium yet, but it will do so at some later time. So examples are, for example, chemical reactions. So on the right-hand side here, you see this. This dish here, and there's some chemical in this dish. And what you see, if this was a video, still have to figure out how to show videos and this notepad application here. But these are waves that progress here, and you have rotating spiral waves here. Actually, not target waves, target waves. So you see that they do some kind of pulsating circular wave patterns here. And this is obviously not an equilibrium, but this system will turn to an equilibrium homogeneous state if, say, the fuel that it's based on is all consumed. That's called the BZ reaction. And of course, another example of a system that is probably isolated is the universe. Yeah, and the universe is very far away from equilibrium, as you can just see by looking at the sky. And but it will approach some equilibrium state of mass and entropy in a very long time. So this is an example of a system that is approaching equilibrium, but it's not in equilibrium yet. So the other kind of systems, the other way of how you can avoid the second law is if the system is just not isolated, but it's open. And by what that means is it's coupled to some kind of boundaries. In physics, we typically call that baths. Yeah, that exchange, for example, entropy, energy, or particles with the system. And these are the kind of systems, these open systems, that we are dealing with in this lecture. Yeah, and probably in your statistical physics lectures, you have dealt with some open systems that were nevertheless in equilibrium. Yeah? So that's why you have all these different ensembles in statistical physics, because we have these open systems that can exchange particles or energy with their environment. Yeah? So a system that is open can still be in equilibrium. So how can we make it? How can we make a system stay out of equilibrium? An open system out of equilibrium. Yeah, so we can consider a very simple example here. And this very simple example is just a particle, this red particle here. And this red particle just follows some kind of trajectory, that is given by some kind of Hamiltonian, some Hamiltonian dynamics. Yeah? And then this particle here will do some ballistic motion, but at some point it will collide with other particles in the same system. And now there are two effects that such collisions can have. Yeah, so the one is that on a macroscopic level, so that if you zoom out a little bit, then you will see that the movement of this particle is slowed down. Yeah, and so these collisions on a long time scale give rise or hinder the motion of the particle, and that's typically what's called friction. So then there's another thing that these collisions do, namely they lead to abrupt changes in the velocity, in the direction of your particle. Yeah, so these repeated collisions act like a fluctuating force that all the time pushes this particle in a different direction. And now we can write down an equation, a differential equation that describes the motion of such a particle. Now that's just a generalization of Newton's law. So that would mean that mass times acceleration, velocity, time derivative of velocity is equal to minus the mass, that's a friction, times v, times the velocity, plus whatever external force you apply to the system. And now comes this fluctuating force, psi, that I mentioned previously. Now, such an equation describes the particles, the dynamics of these systems. It looks like Newton's equation, but we have this weird force on the right-hand side that is described to you in more detail in a few minutes. Yeah, and this equation has a name. It's just, probably most of you know that, it's the Langevin equation. Now, so this Langevin equation has a few terms. Yeah, so not only this randomly fluctuating force, but we also have this gamma here. That's just the dissipative friction. It's called dissipative friction. Now it describes how the sum of all of these collisions decrease the velocity of this particle. And then we have some extrinsic macroscopic force. Now you tilt the system left or right, and then you apply some force to the particle. Now, and we have this randomly fluctuating force. Now, that's the last component. Now, so what is this force? Now, what is this about? Now, so this force is a random variable. Yeah, so maybe you've heard statistics lectures. It's a random variable. It takes a random value at each instant of time. And it's not just any random value, but we know from the central limit theorem that if you sum up a lot of these forces, yeah, then the net result in some time interval will follow a normal distribution or a Gaussian distribution, as we say in physics. Yeah? So the central limit theorem tells us that we're probably doing quite well if we approximate psi of t with a Gaussian or a normal distribution. Is a Gaussian random variable. Yeah, that's already nice because these Gaussian distributions are always quite nice to deal with. So, and what we also know is that this force is not always pushing in the same direction. Yeah, so the average of this force is 0. It has a vanishing mean. You know, psi, average of psi of t is 0. Now, if it has a non-zero mean, you could just absorb it in some other part of the equation. Yeah, and then we have to say something how this force, this random force, how strong it is, and how it is evolves over time. Yeah, so and this we describe in terms of the correlation, the autocorrelation of this force. So, and of course, we make the assumptions because everything is very messy that this force is uncorrelated in time. Yeah, that means that the correlation of psi of t with psi at some other time t prime is some value a, well, that's the strength of the noise, times the delta function t minus t prime. So this is all only correlated to itself. It doesn't have any memory. And this a is just the strength of the noise, of fluctuations, of this fluctuating force. So I will now show you that if this particle, if this system is in equilibrium, then the strength of this force here is already determined. Now that we already know the strength of this force, and particularly I will show you that this force is actually determined by the friction. The force and the friction are not independent quantities. So, and now comes a little experiment because I have to do the first calculation of this lecture. If this experiment fails, because for whatever reason, then it's not so important because it's not, we're still not in the, so to say, real theory part of this lecture that will start next week. But I'm just giving you some intuition about what it means to be in equilibrium and out of equilibrium. So let's have a look at this equation again. The first thing we do is we do a Fourier transformation. Yeah, we say Fourier transformation. We say that this Fourier transform of the velocity of this particle, yeah, as a function of some omega, frequency omega, is, it's just a definition of the Fourier transform, e to the I wt v of t. Yeah, and if we plug this in, just look at the equation again here. So here we'll get some I, the I from the exponential comes down, sorry, I should use the pointer. So here the I from the exponential comes down and the omega as well, because we have the time derivative, and the rest is basically just a linear term. Yeah, so what we then get if we Fourier transform is that we have minus I omega from the exponential here. The Fourier transform is equal to minus m gamma Fourier transform of the velocity plus the Fourier transform of the modes. Yeah, so now we have an algebraic equation, and we can solve this formally. We can solve this formally and say that V tilde is equal to 1 over minus I omega plus m gamma times psi tilde. Now, we can just write that down. Yeah? So, of course, we can't do anything with that, but we can write that down, and this prefactor here is typically called the response function. Yeah, R of omega, and this response function gives how the velocity reacts to a fluctuating force. Yeah. So now we've looked at the Fourier transform of the velocity. Now let's have a look at the Fourier transform of fluctuations, of these correlations in fluctuations. So let's have a look at the Fourier transform of this quantity here, psi of t, psi of 0, now or t prime, say t prime. Yeah, and if we plug that in, now we just do the same trick. Now, psi of omega prime is equal to the integral over dt e to the I wt, and now the correlator psi of t prime. Now, and now to make use of the properties of the Fourier transform, especially the Fourier transform of delta function is just 1, and that we see in the Fourier space this correlations in the fluctuating force are just equal to A. Yeah? And this is sometimes called spectral density. That's not so important.
Excuse me?
Yeah.
The equation on the very first equation, it would be like exponential minus I omega t, right?
Yes. Yes, you're right.
And then there will be on the second line, there will be minus I omega m. V tilde.
Yes, that's correct.
And there will be the m factor will be like in common in the denominator on the third.
Yes, here, exactly. Yeah, that's correct. That's correct. Actually, that's exactly how I have it in the notes. Yeah. Okay, thanks a lot.
Thank you.
May I have a question regarding the previous slide?
This one?
Yeah, so it's really, maybe it's just a very naive question, but the fact that we allow our psi t to follow the central limit theorem and hence follow a Gaussian distribution just reminds me of the Maxwell distribution of velocities, which is one of the crux of thermodynamics and thermal equilibrium conditions. So why do we allow psi to follow Gaussian distribution?
So the psi is the strength, or is a force that's acting at each time point, yeah, on the velocity. It's not the velocity itself. There's a force that's acting on the velocity, and it's just random. So if you have, yeah, you suppose you have a time interval delta t. Now this time interval, you have 10 million forces acting on your particles. Now that means that your velocity is equal to your old velocity, and then a long sum over these 10 million identically distributed random variables.
Yes.
Yeah, it's just a very basic statistical thing that this is a Gaussian distribution. In many cases, it's not Gaussian. There are many examples where it's not Gaussian, but that's typically cases where things get very, very messy. Yeah, so that's well beyond the scope of the lecture. But there's still, so your point with the Maxwell distribution is actually very good, because we still have the V in equilibrium still has to fulfill the Maxwell distribution. Yeah, you still have a constraint. The constraint is not in the Gaussian distribution, but it's in the A, the prefactor. Yeah, so that's where the equilibrium condition goes into, and I'll show you that in the next step here. Yeah. So now we have the correlations and noise, and we can just calculate the correlations and velocities as well. Yeah. V of omega, V of omega prime is equal to something like 1 over. Yeah, if we do the same thing as above, now we get 2 times this prefactor I omega m plus gamma m squared. And then on the right-hand side, we have the force. Yeah. So now what we can do from that is that we can calculate this. Yeah. So we know that the right-hand side here, where's the pointer? This one here is just equal to A. Yeah. And we can now go back to real space, to real time, perform this integral. And by performing this integral, we have to do some contour integral. Yeah. It's not extremely important how this integral exactly works. It's a contour integral, yeah, because you have here something, a prefactor that has some roots. And then you can use residual theorem. So we do here a contour integral. And then we get A over 2m squared gamma. Yeah. Now, in no situation, until now we have assumed that the system is in equilibrium. But if we assume that it is in equilibrium, then the equipartition theorem holds. Yeah? Equipartition theorem, and it states that basically the energy of the system is distributed equally across all degrees of freedom. And this theorem tells us that the kinetic energy gets a fraction of, or is equal to kVt over 2. Yeah? That's now where I put the condition of thermal equilibrium. And what we get from that is just what you see here in this box here. This A, the strength of this fluctuating force, is equal to a term that contains the friction coefficient at the temperature. So by setting this one parameter in the equation, the gamma, yeah, or gamma times m. By setting this in the equation, by fixing this, you already know the strength of the fluctuating force. Yeah, and this is just a manifestation. It's called Einstein relation, and it's a manifestation of the very important fluctuation dissipation theorem in statistical physics. Now, this fluctuation dissipation theorem tells you that the strength of a fluctuating force in your system, or the strength of fluctuations, is given by the strength of friction. And in general terms, you can write this as I write down here. On the left-hand side, you have the strength of fluctuation, or the strength of correlations in V, yeah, or X sign. So these correlations are something like psi omega prime. So that's the general fluctuation dissipation theorem. The strength of this fluctuating force, the strength of fluctuations in my velocities due to this force, is given by this response function, the imaginary part of the response function, and this response function is essentially, in this case, determined by the friction. So another way to read this fluctuation dissipation theorem is that the intake of energy that this particle gets through this fluctuating force needs to be exactly balanced by the loss of energy due to friction. And this is true if we are in thermal equilibrium. And that also means that we can use this fluctuation dissipation theorem to decide when we're not in equilibrium. So, for example, so there's a theorem that states that if we calculate a quantity called J, which is thus just the total deviation in this equation, if this does not hold true, if this is not equal on both sides, then the amount of disagreement tells you something about how far you are from equilibrium. C tilde of omega minus 2 kBt imaginary part of the response function R of omega. If we calculate that, then we know this quantity J, and this quantity J is just the amount of dissipated heat. So if you are out of equilibrium, if you violate, so to say, the second law, you have to compensate for that in your environment. And that means that you need to export heat to your environment. And this is quantified with this equation, and it tells you how far away you are from thermal equilibrium. That's a theorem by, I think, Harada and Sarah. So let's continue with our particle here. So how can we make this now? How can we drive this system out of equilibrium? And turns out it's actually pretty simple. And this there's actually a very specific biological example for that. And these are bacteria. So many bacteria have so-called flagella. Now these are these little hairs here, and the tails. And these flagella can rotate. And when these flagella rotate, then these bacteria can move ballistically, like a little rocket, through a medium, through space. So what these bacteria do, they take in energy from the environment, for example, glucose. They have, for example, glucose. They metabolize this energy and convert it to kinematic. One part of it, they convert it to kinematic energy, to kinetic energy, so that they move in one certain direction. And now we can write down the Langevin equation for that. So we have the same as before, V dot equals minus gamma V plus epsilon kV. Now this epsilon kV comes from here. That's just if you use this energy epsilon here that you metabolize, and you put it into kinetic energy, that's this one here, yeah, then you get a force that corresponds to this one here, epsilon kV. Yeah, so you're going to get a force plus, of course, your collisions with your neighbors. Yeah. The point is now that we have a second friction term that has an opposite sign, but in principle, we can set the second friction term here, that's the total dissipation term. I shouldn't call it dissipation, actually. I should call it dissipation, yeah, but that's the total amount of terms that are proportional to V, yeah, and we can now do the same calculation as before, but now our prefactors are what we called previously the gamma. The prefactors of this V term can take any value that you want. Yeah, it's up to the material to digest nutrients and convert it into kinematic energies. There are, of course, some constraints in terms of chemistry, of metabolism, and so on. There's not a certain maximum amount that you can achieve. But in principle, you're free to choose your epsilon and your k in whichever way you want. You can make that time dependent or whatever. Yeah. So this means that by this choice here, by converting chemical energy to kinematic energy, this vacuum breaks the fluctuation dissipation theorem, and this because dissipation is independent of fluctuations. Now, the prefactor of these fluctuations here is now completely independent of the prefactor of these dissipative terms, and we can get whatever we want and break the fluctuation dissipation theorem. So this theorem is called an active particle or active Brownian motion, is out of thermal equilibrium. Yeah. So what's the general pattern behind this? Okay, we break the fluctuation dissipation theorem, and then we are out of thermal equilibrium. But how can we do that in general? So I think there's a general topic behind that, and this general theme is that you have an isolated system. You couple it to some boundary conditions. So mathematically, we would say boundary conditions. In physics, we say bath. Yeah, and in some cases, this bath, if it's nicely behaved, if it's also in equilibrium, then this whole system will also take an equilibrium state. But if you couple it to multiple baths, for example, a hot and a cold one or so, then your system is out of equilibrium if these baths are not compatible with each other. For example, here in this case of active Brownian motions that we just discussed, we have different baths that couple to the fluctuation and dissipation parts in the fluctuation dissipation theory. So this particle takes up chemical energy and converts it into this movement, by a reaction that typically involves the conversion of ATP to ADP. That's how living systems use energy, so to say. And because this particle moves around, it needs to increase. Because this particle is, let's say, out of equilibrium, it needs to increase heat in the surrounding. So that means it's coupled to a heat bath. It dissipates heat to a heat bath. Now, of course, there are many other examples in physics that you can see. One famous example is turbulence. Turbulence, you probably, if you set saw one of these airplane videos with the turbulence behind the airplanes is a big problem. You have an intuition what turbulence is. And in turbulence, kinetic energy of these velocity fluctuation cascades from some large spatial scales. Now, for example, the scale of the airplane turbine or so, all the way down to some small scales where it's then dissipated. Yeah? So in this case, you have different baths at different scales. You have a heat bath on a large scale, now where you input energy, and then you dissipate this energy on small enough scales. So that's small scales. There's also a heat bath because it takes up energy. Yeah. So if we were in a live lecture now, I would ask you now for suggestions for other systems. And but now only Yiteng is here, and Yiteng, I would always have to ask Yiteng. But so for people who come from biological physics, this approach with the baths, with the coupling a system to bath is not very natural. In our case, we typically define non-equilibrium nature of these systems, of non-equilibrium systems, by probability fluxes, the microscopic level, so to say. But this idea with the bath is also quite general and actually comes from another lecture that I gave last year with a colleague from condensed matter physics. And in condensed matter physics and quantum systems, the idea of a bath is much more natural. And then it's a very nice exercise to translate our favorite non-equilibrium systems in social sciences and biological physics, and just sort of say, and ask actually what are the two incompatible baths that drive these systems out of equilibrium. And in some systems like epidemics and so, these answers is pretty difficult. But maybe we can do that at the end of this this term. Yeah. So with this, I'm finishing the lecture for today. So,
excuse me, Stefan.
Yes.
I work in biological physics.
Yes.
So I do study gene transcriptional regulatory networks.
Mm-hmm.
So for example, you have a transcription factor that regulates a target gene.
Mm-hmm.
So the transcription factor may be regarded as the bath for the regulated gene. Is it so?
Can you repeat the last sentence?
So the transcription factor, is that can be regarded as a bath for the regulated gene?
So one thing you have to think, so I'm not entirely sure, but one thing you have to think about is whether your system consumes energy in any case. Yeah, because at some point you have to use ATP. Yeah, at some point you have to use ATP, and then you have the chemical bath somewhere. Sometimes this chemical bath is hidden somewhere in another place. But my guess is that if it's a non-equilibrium process, so it's a normal enzyme kinetics is in equilibrium. Yeah, so you need to do something like if you modify chromatin, transcription factor modify chromatin, and sometimes you lock that in with epigenetic marks. Mm-hmm. And these epigenetic marks are the such that the irreversible step, or they are the step that require energy. Yeah, so I would say it depends on the transcription factor. Like everything in biology, it's probably very complicated.
Thank you.
Okay, thanks a lot for your question. Are there any other questions?
Yeah, so considering an example of a heavy ion collision in a particle accelerator, So the experiments there, they start with particles colliding at extremely high energies. And then there is a phase that they thermalize, and then the particles also convert into other particles. And that is the sort of the general way how the system evolves. But that has more or less been studied through equilibrium statistical methods. So could you, with reference to today's terms that you introduced in the lecture regarding like the fluctuation, strength of fluctuation and other factors, could you explain with examples on that, with that particular experiment
Okay.
and what?
So it's very so probably so I think probably until now already the coolest thing about this lecture is that we seem to have an extremely diverse audience. Yeah. So we're getting some questions here from particle accelerators. I think in this case the equilibrium is actually fine. Yeah, because you don't inject the energy. Yeah, so you inject the energy once into the system and then you let it evolve.
Yes.
Yeah. So, but you're not like in this particle. You're not this. You're not basically continuously injecting more energy while the collision takes place. Yeah, you inject it once, like in the universe. You inject it once at the beginning, and then you let it evolve, and at some point you'll reach some equilibrium state. So, not being an expert in elementary particle physics, I would actually naively think that equilibrium is actually quite fine.
But isn't it exactly like the example we did before of the universe, which is considered as a non-equilibrium system, which is isolated?
Yes. Okay. So sorry. So the universe is non-equilibrium, of course. Yes, but it's an isolated system, I guess. Yeah. So it's an isolated system, and because it's an isolated system, it needs to obey the second law of thermodynamics. That means you get all the consequences like the entropy increases and so on. So you know that the universe at some very distant future will be in a state of maximum entropy. Now that's what people refer to when they say like entropy death of the universe or whatever. Yeah, so it will reach some state of maximum entropy. And let me think. Exactly. So yeah, I think in terms of the particle collisions, you have to yes, you have to. I think you have to think about timescales here. Yeah.
With respect to the times, I think if you take the limit of t tending to infinity, that really depends on the scale of your experiment.
So for t to infinity, yeah, so for t to infinity, you know that your system will end up in equilibrium if it's isolated, yeah, because you injected the energy at some point, yeah, and then you then you isolate it and see what happens. Now you know that at some point it will be in equilibrium. The question is, how long does it take? Yeah, and that's a question that I cannot answer without elementary particle physics knowledge. For example, in physics, we have examples where systems, you take them out of equilibrium and then you see what happens, and they will never reach equilibrium actually. Yeah, because that's called aging. Yeah, they very, very slowly have a very slow dynamics, and then it goes back. Yeah, so these are systems where you wouldn't say that you would make like equilibrium approximations or so. If you have a system that exponentially relaxes back to its steady state, to the equilibrium state, you perturb it and then you see what happens, but it immediately goes back to the equilibrium state. Yeah,
so like
then
a cyclic process.
So what I'm saying is that with these time scales, yeah, the question is how long does it actually take to go to equilibrium? Yeah, and that's probably a question that is very specific for these kind of systems. Yeah? That said, equilibrium is much easier than non-equilibrium. So it could just be that people just make the approximation, equilibrium approximation, without actually saying that it's actually not an equilibrium. For example,
Okay.
in physics and statistical physics, we have Onsager theory that describes systems that are just a little bit out of equilibrium. And what this theory actually says is that if you go out of equilibrium, then you still have the same kind of fluctuations as actually in equilibrium itself. Yeah, so this is an example where you say, okay, my system is not in equilibrium, but I treat it something like an equilibrium system.
Mm-hmm. And thank you for the answer. And another question is, are we allowed to chop our system, which we know is going to eventually end up in equilibrium, and we chop the system at a certain point of time where it still hasn't reached equilibrium, so it becomes a valid case study for non-equilibrium statistical physics? We deliberately chop it.
Yes, so one thing I have to say that all of these systems are valid case studies for non-equilibrium physics. We just so there's a whole field of this first case of system. Now these glasses, all these glasses, glass dynamics, spin glasses, and so on, neural networks. These things they fall in this. Neural network is not a very good example. But all these glasses are sort of non-equilibrium systems because they, for a very long time, stay out of equilibrium, but at some point they will be in equilibrium. So I'm here talking about systems that or we also say sometimes active systems, that constantly take up energy from the environment. Think about biological systems. They constantly, for a cell to survive, you always have to convert ATP to ADP. You always have to take up chemical energy. Always, otherwise the biological systems can't keep up the complex structures that are going in the process that are going on inside cells. Now, once you stop this process, the cell is dead. So I'm here talking about systems that constantly take up this energy, and at any instant in time. So regarding your question, once you're out of equilibrium, it's very hard to make general statements. It's not like an equilibrium where we have our partition function, and then we have phase transitions and renormalization and criticality and universality. These kind of things are much more difficult in non-equilibrium systems. So to answer your question, probably the answer depends on what exact system you chop up. It's quite likely that there's no general answer to that.
Okay, thank you.
Thank you for your question. So, are there any other questions? So, if there are no other questions, if you have any feedback, so just send me an email this week. I'll try to implement it. And also, if you have anything that's useful for you that you want to learn in this lecture, just also send me an email. So I can't promise that I'll be able to implement that because it's already quite tight, the term. But this lecture is, so to say, also a little bit an experiment. So what are actually the tools that we need to get some understanding of these non-equilibrium systems? So what are actually the fundamental concepts that we need to understand? And the answer to this might be quite different for each of us. And I would be quite keen to learn about what's your background and what are you hoping to get from this lecture. So just send me an email, and with that, see you all next week. So if there are no questions, then I'll close the lecture, and see you all next week, same time. Okay, bye.